So in this video, we are asked to decide the isomorphism types among these four groups. So what that means is we have to decide which of them are isomorphic to which other ones, and if possible, give an isomorphism. If not, explain why not. So a couple remarks before we jump in. First is, if I prove that A is isomorphic to B and B is isomorphic to C, we just saw in the last question that I know that A is isomorphic to C via the composition. So I don't need to work out every possible relationship between these groups. I just need to figure out which ones are isomorphic to which ones not, and then employ that transitivity result. Second is, I don't think we've encountered this piece of notation yet. This asterisk, this star, means that the group operation is multiplication. And we don't use the full Z mod 7Z. We only use those elements that actually have multiplicative inverses. Now, because 7 is a prime number, it will turn out that that is all of the elements except for 0. So it's these elements, mod 7, under multiplication. But in general, it's not completely obvious. Like if I did this with 8 instead of 7, which elements would have multiplicative inverses? You'd have to go and check that. So without any further ado, let's take a look and see what we can figure out. So the first thing that stands out to me is that these three groups are all commutative groups, right? Abelian groups. This one's not abelian. And so S3 cannot possibly be isomorphic to any of the other guys. So that's good, right? This one's fenced off. We have to figure out then, what about these three? What isomorphisms are possible between them? Well, I happen to know from a lot of group theory experience that these two groups, we'll call these guys A, B, and C, that A and B are isomorphic groups. And I'll show you the isomorphism. The isomorphism will actually go, actually no, A to B is fine. So let's do phi from A to B, which sends 1 to 1, 1. And then it continues in such a way that the isomorphism equation is forced to hold. In other words, phi of 2 is phi of 1 plus 1, which is phi of 1 plus phi of 1. And then in that way, we just keep going to define all of them. So 2 goes to 2, 2. But in the second slot, if you have a 2, we're working mod 2, so it gets reduced to 0. 3 becomes 0, 1. 4 becomes 1, 0. 5 becomes 2, 1. And 6, which is the same thing as 0, goes to 0, 0. And so I have concocted this in such a way that I have enforced the isomorphism equation to hold. I just need to see that this is a bijection. And we can see that all 6 of these entries are different. And so it's got to be a bijection. So that handles A and B. So what I have to do now is decide, is C in the same club as A and B, or is this a new isomorphism type? And since the operation here is different, it's multiplication, the simplest thing that I can think to do is to take a number which is not 1, because the powers of 1 are boring, and look and see if any number has the ability to generate the entire group. So we haven't done like a deep dive into generators yet either, but you notice here that in Z mod 6Z, everything is a multiple of 1. In Z3 cross Z2, everything is a multiple of 1, 1. Even though like 2, 0 doesn't look like a multiple of 1, 1, it is, because it's 1, 1 plus 1, 1. And so we could ask then, is there an element in C with the same property? So let's look. What are the powers of 2 in this group? We have 2, we have 4, and then 8, but 8 mod 7 is 1. And then we loop around. And so 2 doesn't do it. What about the powers of 3? We have 3, and then 3 times 3 is 9, which is 2 in this group. 2 times 3 is 6. And then 6 times 3 is 18, which is 4 in this group, mod 7. And then 4 times 3 is 12. Man, multiplication today is hard. And 12 is 5 mod 7. And then 5 times 3 is 15. 15 is 1 mod 7. And you see, we have all 6 powers here. So all 6 elements are actually powers of 3. I think that was a little bit surprising. This tells me how to define an isomorphism A to C. So we already used the letter phi, so we'll use psi. Phi A to C goes by sending n to 3 to the power n mod 7. Because 1 will go to 3, 2 will go to 2, 3 will go to 6, 4 will go to 4, 5 will go to 5, 6 will go to 1. Really surprising how much of the order is preserved, but nevertheless, this must be a bijection because, again, I cooked it up in such a way that the isomorphism equation is forced to hold, right? Because it's just laws of exponents, right? Phi of A plus B would be 3 to the A plus B, which is 3 to the A times 3 to the B, or phi of A times phi of B. All right. And so this proves that C is also in the club. So we got these 3 isomorphic, that one by itself.